So this morning we had our first two giveaways. So the Go Builda $50 store credit was given to team 15524. And then for our second giveaway, team 10528 won the Servo City $50 store credit. And during the afternoon, we're also going to have two more giveaways. So we're going to have a Go Builda 1121 series low side U channel bundle giveaway. And then we're going to have a Go Builda 5202 motor giveaway. And then also we have a survey respondent drawing. So the survey link will be in the chat. And if you guys do the survey, we're going to put you in a drawing for these monitors that were donated by local tech companies. So I'm going to start the first presentation of the afternoon session. And if you guys have any questions, you guys can go ahead and leave it in the Q&A session. Okay. So I'm going to talk about FTC teams helping the communities during COVID-19. These are some things that my team and some of the other teams have been doing. So the first thing that our team did was 3D printing PPE. So when all of the pandemic stuff happened, our team was looking for a way to help the community using our robotics knowledge. And we noticed that there was a shortage of PPE, and a lot of other robotics teams were using their 3D printers to print face shields and ear guards for the community. So we wanted to do that as well. So we kind of set up a process to do that. And we also had other teams join us. We did daily virtual status calls within our team to prepare all of this. And at our peak production rate, we had 40 to 50 face shields per day and 100 ear guards per day. So these are the Budman and Prusa models. So we took these public available models and made improvements. As you can see, the slits on both ends to keep the clear film in. And then we sent these models into the field to doctors and nurses so that they could test the models. So these are our 3D print makers. So once we started receiving a lot of requests, our team couldn't handle all of them at once. So we looked for other teams in the area to help us, and these are the teams that jumped in to help. So first we have Rice Ravenclaws 11472 from Rice Middle School, Smarty Party from Hedrick Middle School 166, Technical Difficulties 7172, which is community team from Plano, Vibots 11341 from Vines High School, and Chain Reactions, which is an FRC team from Plano Senior High School. And with all these teams, we established a Slack channel, and we drive back and forth to pick up the PPE with them. And at the beginning, when we hadn't figured out all of our fundraising yet, the Rice coach also lent us filament, which was really helpful. So these are some pictures of the 3D print makers. As you can see, everyone works from wherever they are, and then we use Slack to communicate, and then we also meet with each other to pass the PPE. So on our team, we also have different sub-teams. We have an assembly line. So the assembly line is in charge of picking up the 3D prints and materials from the makers. And then they assemble these face shields and drop the face shields off to the pickup location. We also have a packaging and sanitizing team. They sanitized all of the assembled PPE with UVC light and packaged it with an airtight seal. Then the PPE goes to our distribution team. They distribute all the face shields and ear guards to local clinics and hospitals in need. We also have a request processing team. They're in charge of taking orders in from the clinics and hospitals, and then they also check the waiver forms and communicate with the distribution team and the clinics and hospitals with all of the pickup information. And this is our material research team. At the beginning, when we started all of this, they researched all of the best materials and found the best types of face shields to print. We also have a 3D printer maintenance team, which really uses our robotics knowledge. So this team maintains all of our 3D printers, and they fix the printers when there were problems. And we also collected some broken 3D printers and fixed them and started using them as well. So through all of this, we've donated over 2,000 face shields and 3,700 ear guards to over 40 clinics and hospitals in need. And these are some of the hospitals and clinics that we've reached. So in the future, if any other teams would like to be involved in 3D printing PPE, you guys can contact us at technicbots.team@gmail.com and we can give you all of the details to get started. Another thing our team did was the virtual robotics fun hour. So this is a weekly robotics fun hour that our team hosted every Friday for participants at home so that they could learn about STEM and robotics during the pandemic. So a typical robotics fun hour has an online resource, which is a type of STEM or robotics related resource that we share with the participants that they can play with and learn from at home. And then we usually had a builder zone, that's a hardware or related topic. And then we had a CAD topic, and CAD is really good for virtual events because everything done in CAD can be shared virtually through Zoom. And then we also had our RoboCode section of the hour. And RoboCode is a virtual robotics coding platform. And we had RoboCode tournaments every single week. And also we had our annual Youth Robotics Fair embedded into this virtual event. So our team mentored all the ACP First team members virtually through Zoom, and they worked on their projects to demonstrate at the Youth Robotics Fair. So these are some of the participant comments. We had a lot of them say that they really liked how a lot of ages were implemented, and we showed a lot of different levels of robotics, and they also really enjoyed the RoboCode. So this is an example of what a typical RoboCode tournament would look like. This was actually our final tournament, and we also have a link to all of our event recordings and slides on our website. So I'm going to go ahead and play this video.
But that was impressive. This time, Spinbot, again, unfortunately, gets taken down really quickly. My second robot is fighting Shepard, and Icon Field is fighting Baldi. But it seems that some bullets are slipping from some fights into the other. Shepard rams into my second robot and quickly takes it down. Baldi appears to win against Icon Field. Now it's just Baldi versus Shepard. But it looks like Baldi shots. Oh, Baldi hits a shot from being disabled, takes down.
So that's an example of our RoboCode. So does anybody have any questions about the COVID-19 efforts? Okay. If not, then we can go ahead and begin our 2 tracks. So we have a beginning track and an advanced track. So if you want to stay in the beginning track, you can go ahead and stay in this Zoom webinar. And then if you want to go to the advanced track, there will be a link to the Zoom posted in the chat. So you guys can go ahead and click on that link if you want to go to the advanced track. And then for our beginner track, our hosts are going to be Everett and Victor from team 18227. So I'm going to go ahead and hand it over to them.
Okay, thanks, Melody. So, hi, welcome to the beginner technical track. And just a reminder, if you need to ask questions during the presentations, either raise your hand or ask in the Q&A, and your questions will be answered. In the chat are all sessions. Yeah, the sessions are going to be recorded and posted. And be sure to put your team number in parentheses after your name. Or if you are a rookie team and you don't have a team number, then make sure to put an abbreviated version of your team name behind your name. So you can do that by leaving the webinar, then rejoining it under that different name. So I think without further ado, let's get started. So, sorry, we will also need to take attendance 10 minutes before the giveaway, which will be at 3:55. So make sure you change your name by then. Yeah, so now let's get started. So I think first we have FTC Simple Java 101 with Onbot Java by Ian from 15536. So Ian, I think you have the floor.
All right, thank you. So let's see if I can share my screen real quick. Can y'all see me and hear me okay?
Yep.
All right. So welcome to FTC Simple Java 101. I am Ian Flores, as he mentioned, from team 15536. Now, some of the objectives I'll be hitting today is how to pair phones to each other and then to the computer. That part will run by pretty quick. I'm going to be focusing today more on the programming aspect for y'all. So pairing phones, you have to make sure that you have the corresponding apps. You have to have two phones needed, which is in FTC, you have the robot controller and the driving station. Make sure you have both phones on airplane mode with Wi-Fi on, and that they're obviously charged and ready to go. So the procedures you're gonna have to have them linked up is on the robot controller, you're gonna get into the app, you're gonna wait for a status that says running, and then on the driver station, you're gonna open up the app, press on the three dots you'll find on the top right. I'll have pictures for y'all. And then select settings, select pairing method, select Wi-Fi direct, go back, and then you want to connect it to the robot controller. For the naming part on whenever you're naming your robot controller and driver station, you want to name it, usually it's done based on your team number and then what phone it is specifically. So in my case, our phones are 15536 RC and then 15536 DS. So as I mentioned, this is the robot controller. It says running, and then on the driver station, you go into settings, you pair it up through Wi-Fi direct, and then you pair it to the driver station. You select your own. It's gonna show up with yours name. This is the important part. You want to name it yours. That way you don't interfere with any other teams. And then once you're all set, it should tell you the network that you're with, and then you're gonna have two button downs that will open up to all the programs that you have. There's the autonomous side and then the teleop side. I'll be going more into depth for each one. Then once it says your network is active and connected, you're ready to go. Now, whenever you're gonna code, usually you wanna pair it into a computer, that way you have a full view. To access that, you're gonna connect your RC to the laptop Wi-Fi, or the other way around, your laptop to the RC phone, and you're gonna hit program and manage. Now on Chrome, this is a number that you will always be seeing, 192.168.49.1:8080. In case any errors, you will most likely be because it will tell you, like on the Onbot Java screen, it will tell you it's because you're not connected to the phone. So you want to make sure your phone is connected. Are there any questions so far? I can't see them if there are any.
Yeah, there's a question in the chat that is, do you need an RC phone if you are using Control Hub?
If you're using control, yes, usually you will be using the robot control. Well, actually, no. I believe so. I have heard some things about it. I am not fully sure about that, but I would suggest just connecting them to be able to program on the laptop. So now getting ready to actually program in Java, on Java. So in the programming world, you're going to find a lot of things from the syntax that you'll be using, your organization, the classes, methods. Now, a good thing to know whenever you're coding is you want to know what you're doing and what's your game plan. So if you want to have your robot move forward, you're gonna that's your goal. If you want it to go down and back, that's your goal. You just got to know what you're doing, or else you're not gonna be able to function very well. So as I mentioned, there's an organization within that it takes place. I will be helping you guys out on how to you will be where you need to put specific items, and it's like an essay or just a school binder. It's gonna have tabs. You're gonna have your sheets of paper and like your notes on each part. So this will be just a show. This isn't the actual OnBot. This is an IDE called BlueJ. I used it a couple of years ago. And so this is your workspace, what you're seeing, and then that's so that would be what's your file, your whole entire where you find your program. All each box is a little tab looking item. That'd be your tabs in like a binder. That's your class. And if you open it up, you're gonna find all these items. That's where you're gonna find your main code. So that'd be your class, the main screen now, your workspace. You have your methods, which would be the yellow boxes. That's well, you'll find your statements all compiled together. There will be a main method, which you'll be coding in, and then you have keywords. Now create a not mode. So once you open up OnBot Java on that link that I told y'all, it's gonna open up. You're gonna have to look for a spot that says OnBot Java. You're gonna tap on the plus sign. You're gonna name your file on where it says file name. You wanna make sure that starts with an uppercase. You're gonna come down here, select whether it's autonomous or teleop. This is the important part. If you wanna have this program to be an autonomous program, you'll hit autonomous, and once you're on the phone, you will click on the left side of the button to find your program. If not, it's gonna be on the right side with teleop. Are there any questions so far? I can't see the chats. Give me a sec to find whether there are any questions.
I don't think there are any questions so far.
Okay. Okay, so and then within that, there's samples. That's a great way to learn on how to code new things. FTC provides many types. Usually this linear op mode will help you with just the basics. Within that, you can learn how to use the gyroscope, IMUs, time, and just be able to program more efficiently. So if you're not sure on how to code, that's a great way to start also. So you create a file, but now what? Write and program. So at first you're gonna see like it has a ton of stuff or nothing at all. Usually it's a ton of notes. It's not actual code, so don't worry and don't overwhelm yourself. If you scroll all the way to the bottom, once you open it up, you're gonna find this small, about 13 lines of code-ish, which it's just a basic setup, which will, once you run it, it would just tell you status initialized, and then it's just gonna, your robot's just gonna stay there. So the next step would be inserting your actual code. So there are Java keywords and variables. The keywords is what would be a defined meaning. So like any words in English language, there's like int, return, public. You're gonna be using though mainly ints and objects. You'll definitely be using objects. I'll explain what that is in a bit. But you're gonna have also variables, which will be your objects put together. And once you set them all together in this complete syntax, then you'll actually be able to start making the robot move within those things. So what this, oh wait, yeah, right. Comments. I'll explain more into how you put them together, but comments are a good thing within coding. Coding, whatever you're coding, you're gonna be sometimes having a ton of lines of code and you're not gonna know which one's which. So it's good to insert comments. You can put on the sidelines saying, this part is what makes the robot turn. This will make it go forward for 3 seconds or whatever that specific line is. You can also comment out your actual code, which will then just mute it and you can run it without that part running specifically. So the way you would do that is either place 2 slashes or a slash and an asterisk followed to closing it with an asterisk and a slash. So now back to coding, the actual part. whenever you're coding, the first thing you want to do is create your initial variables, which would be known as stating. So over here, you're going to see the first part you usually want to have for your robot is to have it move. So you're going to need 2 motors at least, which would be a right motor and a left motor. They're DC motors typically, and so this would be what the object will be, a DC motor in this case, and then the variable name would be a right motor. And then for the next one would be a left motor. You want to name your objects usually to what they are. So if the motor will be used for an extension, you want to name that extension. If it's for just a simple hook, then you name it hook. You want to know what you're talking about within your own program. Next would be the hardware map. After you create your initial variable, you want to instantialize it. I believe I missaid that. You want to initialize it into the hardware map, which will tell the object this is exactly what it is. You can't just create something and say, oh yeah, it's definitely that. The code won't recognize it that way. So you have to tell it exactly what it is. And you're getting that from the hardware map, which you find on the phone. This will tell it, okay, once you run it, it's going to say, oh, this is a DC motor, and I can find it within the phone saying, oh, it's a right motor. So you got to make sure it's within the phone. If it's not already programmed within your phone, which you can find through the settings on the hardware map whenever you're setting up your code, or not your code, your robot pieces, it won't find it. So you want to make sure everything's already in there before you actually start coding. So now a quick adjustment before you actually have the robot move. You want to make sure you have 1 wheel set forward and 1 wheel set back. Else you're just going to have it spinning in circles once you have it start moving. You could overcome this by simply putting the power to just negative and positive. But to have less problems, you're just going to set 1 wheel reversed to whichever way you want to have forward. So that you would find that through the dot set direction method. And then you just want to label 1 forward and the other 1 reversed. For the actual movement, this is where you call in a few methods already inserted. There are 2 ways within FTC. There's the driver control period and there's autonomous. So one way you could do it is through getting constant input, which would be through the gamepad. And you could, whatever buttons you feel like it, literally. Usually it's typically the joysticks. So you call the joystick you're using, either the x-axis or the y-axis, and then you set it to move. Else, if you're using autonomous, you're going to set values forward. For the motors, they can range from -1 to 1, and it's only in decimal points. There's nothing higher or lower. You want to place that within the op mode is active, else it will only do it once, which is this line right there. Are there any questions right now so far on the chat part?
I don't think there are.
Okay, thank you. So turning, obviously, whenever you're turning, you want to have something affecting it. So in this case, what you typically use is the same stick. You want to have it the y-axis, which would be your front and back. And then you're going to have the x-axis, which has it move side to side. So you're going to create another part which tells you, okay, it's going to get a number depending on where your x-axis is, and you're going to add it to one of the motors and subtract it from the other. This depends on how you're wanting to use it, which way you want it to be right and left. It depends again on your direction, but typically you're going to set 1 plus and 1 minus. This will cause for the road to set the power to a different speed, and that's how you turn. You can't just turn with the same speed. One has to be faster and one has to be slower. Finally, for whenever you're getting into more complex, you want to build methods in order to reduce the amount of space. This is typically done for autonomous. In autonomous, you're not going to be wanting to write the exact same code all over and over. This is whenever methods come in handy. You want to create a method that just is a simple task, usually, and that task will be repeated throughout multiple times. So in autonomous, usually you're going to move. So creating a movement method would help to set that to whatever how far you want to move. Methods can be set to void and return methods depending on what you want. If you want to get a value, then that's whenever you use a return method. Now, programming it autonomous, there are multiple ways you can control your robot through autonomous. There's time, there's distance, gyroscopes, visuals. It just depends on what you have available and what you want to use for your tasks. I'm not going to go into depth for this because I'm not a full-on expert. And this is something I can't specifically say I'm good at. But I do know some basic parts to it. So for the timed, you would have to insert your time. How far do you want to go? For how long? And you're going to have a timer. Then within it, you're going to have another while op mode is active. And it's just going to be checking for how long it's been running. And once it reaches that time, it's just going to shut off. So that's helpful for in case you don't have specifically a distance way you can check it, which would be through an encoder. But as I mentioned, it's usually not as effective as distance. You usually want to get in a distance, which would require encoders. I won't be going again into that detail, but I do have a bit for helping out. So what you would want for a distance is you want to have the position and the final position. It's going to be tracking those until they match, or how far it's traveled, it's already past it. That's whenever it shuts off. Gyroscopes and IMUs, that's more of a directionality type of movement. You want to set a specific angle, and it's going to be checking, okay, am I following the specific angle? And this is used whenever, like, in case something bumps into it, or your robot has a specific motor that has less power. So this would just, once you set it to the angle, it's gonna, with the control hub, it's gonna be checking on which way it's facing. So if you set it to 0 degrees, it's gonna stay at 0 degrees. This is helpful for keeping it, again, as I mentioned, in case it ever crashes, it still goes straight instead of going over into the wrong direction. So final comments would be, for me, it may be hard, but with practice, it can be perfected. And you always want to test your code no matter what. Are there any, I have some, in case you want to reference back to the slides, here's the link, and then I have a QR code if y'all want to, I'll leave it up for a bit. And are there any other questions about it? Let me check real quick. No, I don't see any questions. So I guess that's it from me. I'll be passing it back to you, Everett.
Okay. Thanks, Ian, for that remarkable presentation. So now we have a presentation by Hank and Isaac from 18227, and they're gonna talk about PID controller with onboard Java.
Okay, I hope you can see my screen. So, like Everett said, we're going to be presenting PID controller with onboard Java. I'm Isaac.
I'm Hank.
We're both programmers, and we're both 7th graders at Rice, and we both have 2 years in FLO experience. So for agenda today is, first we're gonna explain to you the concept of PID and why we need PID in FTC. And we're gonna show you how we convert the PID we've learned in FLO into FTC codes with a little data logging to help analysts. Then we would like to give you 2 detailed cases, how to learn PID to control the robot to go straight and turn a certain degree. So what is PID? PID, or proportional integral derivative, is a controller algorithm where it corrects the difference between target and sensor inputs, aka the error. It's the control loop mechanism employing feedback that is widely used in industrial control systems. And a variety of other applications requiring continuous modulated control. PID provides a continuous variation of output within a control loop feedback, removing oscillation and increasing process efficiency. From the chart, you can see there's a closed loop from the final measured output, YT, feeding back to the beginning of the loop for comparison with the set point value, which is the target. The chart is based on continuous calculus, but do not worry about the advanced math symbols, because in later codes, they're simplified computation in discrete form. Why do we need PID? The challenges in the first 30 seconds are different in seasons. The robot may be required to do stuff like identifying a special stone or gathering randomized arranged cubes/balls. So for all these tasks, the navigation of the robot needs to be consistent. In autonomous, we would sometimes need a turn or we need to travel some distance. With this said, we need a PID code to make the robot go straight or turn accurately in autonomous mode. In teleop mode is the time after the 30 seconds of autonomous mode, is when you can pick up your controller and start driving your robot manually. For example, last year you needed to stack stones and you needed a linear lift, and you can use PID to control how far the rack goes.
How we learn PID in FLO. In FLO, we use EV3 blocks to write our first PID algorithm with the same purpose was to keep our robot moving straight. As you can see here, the blocks are not the best way to describe the PID algorithm because there are lots of blocks and wires twisted together and it's not easy for beginners to read. Hopefully in advanced programming languages like Java, we're expecting to describe the same algorithm with much fewer lines and a clear code structure. And we also have the logging functionality built into the block. So we have the PID and sensor data gathered for us. Open this link. As you can see in the columns, we have 5 columns: gyro, which is the input, P correction, I correction, and D correction. This was the live data we gathered from our EV3 robot running lines. On the bottom, there's the algorithms. So corrections are over there. And how we read the charts, as you can see, the line of gyro input indicates where the robot is going to by angle. And the correction calculated and applied to the motors tries to stay the robot on track of degree 0, which is going straight. By specifying different Kp, Ki, and Kd values, the Pi and D corrections contributed in different ratio in the overall correction. I will also use the highlighted lines in later slide.
Translating the PID algorithm in Java. On the left, there is Hank's PID algorithm. On the right is my part of the code. In Hank's code, he had a forgot factor, while I assumed the forgot factor of 1 in my final code, which does not change my accumulated error. The two codes are pretty much the same in terms of calculation, but look very different. My part is organized with separate PID, as you can see in the right, but it's kind of long, while in Hank's code is shortened but compact. For the current error is fixed by P, proportional. I, integral part, is fixing the past error, or as you can see in my code, the accumulated error. Note that in Hank's code, he had a forgot factor of something usually given smaller than like 1, like 0.9. The forgot factor cuts off some of the past error, which is quite suitable for missions, like keeping straight lined. But in my case of turning, the accumulated error plays an important role that I do not want to cut off. We'll mention more details in later slides. D is calculating the changing rate of errors, which is trying to predict the future trending of errors. And most importantly, you add every part together to get your final value of correction. And the factor of Kp, Ki, Kd would control which proportion matters most in your final correction. And they may be fine-tuned to fit different tasks, as you will see later in our 2 cases.
About the forgot factor. Forgot factor is useful in some of our missions or I don't want to keep the integral portion for a long time, but just within a certain time window of the memory. You multiply the ki by the forgot factor, which in this case is 0.9, to get the new ki. As you can see from the charts, by constantly multiplying the factor number smaller than 1, the existing memory will diminish if no errors accumulated. Test the algorithm with the same data. Here is a test program I use to see if the algorithm works. I print out the PID values for the same numbers as EV3 PID uses. On the top right, you can see that the highlighted lines are the same from the chart we saw last. I got almost the exact same values for the PID, which means that the algorithm works. If one algorithm is seeing the same input, which is gyro, and generating the same output, which nears the overall correction, that means that the algorithm in Java should be the same logic as the EV3 blocks. How to dump data for analysis. So I will do a demo on this, and Isaac will post a link in the chat. So as you can see here, this is the first step of getting the logging code to work. So you want to copy and paste this code, which Isaac will put in the chat. After, you can customize this code to fit whatever format you want. And then after you do that, you can go into your main code. You need this function. You title like it, what your title of your code, and then you do throws exception, logging.setup, and logging.log no format no method, which is the format I used. So for logging no format no method, all you do is put quotation marks and then put the variables you want to log in the quotation marks. Next, you want to have ADB set up, but I'm not going to show you that because it's going to take too much. So after you have ADB set up, which you can just look up, you can just do ADB connect 192.168.43.1 and then colon 55555. And mine's already connected, so I'll say already connected to 192 for me. So then after that, what you want to do is ADB show. It will say error close the first time, but after you do it again, you have RK3328 box. You want to do CD/SD card, which basically gets into your SD card where the logging is stored. Do ls-l-t, which sorts the time in the order the logging was made, and it gives you this list. And as you can see at the top, you have logging.txt. So after you know that file, you can basically change the name of that file to put into a different folder, like documents. For example, see, this is the code to do that. ADB pull. You specify the folders and the file, and then you dash. And if you've done this before, you can just click the up arrow until you get it again, and then you can name it whatever you want. So I just name it that. So then if you want a chart, if you want to see like the data, you want to go into Google Sheets. You want to create a blank one. I'm going to go to the File tab, and under that tab, there should be Import. And it's going slow right now for me. Okay, I'll upload. And then I will go in my Documents folder, click on the document I want, and then you always want to do Replace Current Sheet, because if you don't want to replace the entire spreadsheet, and then you get this data. After you get that data, if you want to create a chart, you click on a column, hold shift, and go to the right until all columns are highlighted. Then you want to go to Insert tab and click the chart button, which I believe is loading, and then you get this data. And then you can make corrections based on how the chart looks and if you can read the chart, what to do next. And that's basically how you log. How we use PID. So the first case is PID move straight, which basically just goes in a straight line. The top left is my first chart, which I had without the D control that I logged. The KP is 0.2 and the KI is 0.00043. As you can see, the input is shaking very much. This is due to the high value of KP. If KP is too high, the robot will shake, but you can use KD to lower the shaking. So because of the KP being too high, I decided to lower it to 0.14 in the next chart. So on the bottom left, you can see the next chart, which I also increased KI since the robot was going to the right and you increase KI in that case. So it basically shows that the input's still shaking and still to the right, but it's overall better because it corrects more and has more correction to correct than the first chart. The chart on the right is the best data, as the shaking is well retained into the range of 0.5 and negative 0.5 with a combination of KP, KI, KD. As you can see from the chart, the blue line is much less wavy than the other two charts. So the bottom left chart was to the right but shaking. So based on that, I increased KI to 0.03 and put KD to retain the shaking. It worked well and the result was almost a perfectly straight line. Okay, I'm going to demo. Okay, so I will first demo encoder drive, which if you don't know, is just the robot moving straight without any PID. So this is encoder drive. As you can see, it's very off to the left. So like, it's because the chassis is not very ideal for this. It's too off to the left. But then if you use PID, it will shake, by the way, since the chassis is not ideal for this, so it kind of has to shake. So if you resist against it, it'll also have resistance. So as you can see, it's very much better because it shakes, but it's much more accurate. So that is my demo.
So my Hank's code was to turn straight as you can possibly can. My part of the code is to turn perfect to 90 as I can with PID. As you can see, there are differences with both charts. Without KI, the long term for error will not be eliminated. The gap is always there if you don't introduce the KI. Also, you see a difference where the chart without KI has a jagged line trend, which means there are shaking, and that's not good. But in the second picture, it's very smooth because the different KI values smoothen out the overturning or shaking. And in competitions, if it overturns, it takes time for it to turn back into perfect 90. So we want to avoid the overfixing from the other side. But in dry straight, you can correct it both ways. I'm going to show you a quick demo. So as you can see, the robot is lined up. And this is the code without, this is the code with PID. And it's turned not to 90. And let me show you a difference. So this is the robot without PID. It's just P control. Turn only. As you can see on the screen, you see the heading, it says 00, but actually it turned 90. That means the robot has got stuck. So in the video, the robot kind of got stuck, as you can see.
Credits. Credits go to the FTC 8565 Technic Bot, which was our mentoring team. Byron and Anthony, which were our mentors, our parents, and our coaches. Does anyone have any questions? If you have questions, feel free to either email this email or just put them in the Q&A or chat. Thanks for listening.
Thank you.
All right. I don't see any questions, so I think we'll move on to the next presentation. But before, just a reminder that we'll be taking attendance for the giveaway 10 minutes before the giveaway, which is at 3:55. So make sure you put your team number or an abbreviated version of your team name behind your name in the Zoom in parentheses. So our next presentation is by Evelyn from 18227, and she will be discussing automation in teleop with OnBot Java.
My name is Evelyn, and today I'll be covering automation and teleop with OnBot Java. A little bit about me. My name is Evelyn, and I'm on the FTC team, Area 52. I'm programmer and engineering notebook manager, and I'm an 8th grader. My past experience includes 1 year in FLL. Today, I'm going to be talking about why use teleop automation, the teleop program flow, and I'm going to do 2 demos. First, I'm going to do a demo with 2 servos moving simultaneously, and second, I'm going to do a demo with 2 servos moving in a strictly ordered sequence. Okay. The first thing I'm going to talk about is why use teleop automation. First of all, what is it? Teleop automation is running multiple lines of code simultaneously instead of going in chronological order. Why do we need an FTC? For example, if we want 2 servos to move simultaneously, and I'll do a demo later. First, I'm going to explain teleop in a little more detail. According to whatis.com, asynchronous describes the relationship between 2 or more events or objects that do interact within the same system. So in this case, they would be interacting within the same program, but they do not occur at predetermined intervals and do not necessarily rely on each other's existence to function. For example, if we look at these 2 servos, they are not coordinated with each other, meaning they could occur simultaneously or not, because they each have their own separate agenda. And teleop mode is the asynchronous operation in loop. If we look at this visual representation of a code to move servo 1 into position and move servo 2 to position, we would code it something like this. Servo 1 dot set position to 1 would rotate this servo like it would spin the top. And then we would think that servo 2 to set position to 1 would rotate this servo to its position. However, while we may expect this servo to spin and then stop, and then this servo 2 to spin and then stop, it will not work in the expected order. Because if we look at the way that teleop works, it will run this line of code and it will send a message to the robot saying, oh, you should move to servo 1, you should move to position 1. But it will return immediately before servo 1 actually starts moving in position. And then the code will immediately send a message to servo 2 to say, you need to go to position 1. And then it will return immediately before servo 2 actually starts moving into position. How that will look on the servos is that this servo 1 will barely begin moving before servo 2 receives the message, and then servo 2 will start moving. And to the human eye, it looks like both of them are rotating at exactly the same time or simultaneously. So why would we use teleop automation? Teleop involves human-in-the-loop control during the intensive FTC field competition. And the reason why we use it is because teleop programs make the driver's task easier. For example, if there was a predefined button, A, so this button right here, to simplify a difficult 3-step function into one button, if we wanted to move 3 servos at the same time, the driver could either press X, Y, B at the same time for these 3 servos to all rotate, or it would be easier for them to just press one button A and then have all 3 servos move at the same time, because we've pre-programmed this button A to run a teleop program where all 3 servos move at the same time, like in this example right here. So let's take a look at the automatically generated code. I created a test file and I set up the code for the blank iterative op mode, which is how teleop works. And we don't need to worry about this stuff right here. It's mostly because we're not going to program anything right now, we're just going to take a look at the basic skeleton of a teleop program to see how it works. The stuff the code I've put inside this red box is what we're going to focus on right now. If you look at this comment right here, it says the code to run repeatedly after the driver hits init, but before they hit play. And then later on in the code, it says code to run repeatedly after the driver hits play, but before they hit stop. And if we take a look at the 2 snippets of code that I got from what I circled in red, and this flow chart right here, first we're going to pick an op mode that the driver will select an op mode, and it's basically selecting what program to use to run on the robot. And next, the op mode object will be instantiated by the class variable definition. And here's where the program starts. First, the robot will wait for the driver to press init on the phone right here. And it will keep jumping back to wait for the init button, and it will keep going in this loop until the driver pushes init. And once the driver pushes init, it will activate the code to run repeatedly after the driver hits init before they hit play. So whatever code is inside these brackets will repeatedly play in a loop until the driver pushes play on the phone. And once the driver pushes play, it'll activate the code to run repeatedly after the driver hits play, but before they hit stop. And it will be in this loop. And then this code will be in the same loop, and the robot will wait for the driver to push stop. And once the driver finally pushes stop, the program will end and the robot's motors will turn off. I'm going to do a demo for 2 servos moving simultaneously. And here is the code. It's pretty simple. We're just moving servo 1 to position 0 and servo 2 to position 0. And this is what I put in brackets right here for the code to run repeatedly after the driver hits init, but before they hit play. So if you look carefully, I press the init button, and then the servos will execute, and the code will be executed. And after the code is executed, it will wait until I push play before and before ending the loop and moving on. And now I'm going to demo a strictly ordered servo sequence. So earlier in the other demo, I demoed a sequence that where the servos spun simultaneously, but you might be asking, what if you want the servos to go in an ordered sequence instead of all three rotating simultaneously? That's where the state machine comes in. This is a pretty simplified version of a state machine, but there's 3 states here, and this is the initial state, state 1. It will wait until the trigger event 1 before transitioning into state 2. And state 2 will wait for the trigger event 2 before transitioning into state 3. And finally, there will be a trigger event 3, which will return the robot or whatever into the original position, the original state. And here's an ordered sequence. So servo 1 finishes rotating before servo 2 begins to rotate. So if we start from right here, I'm going to press play, and then the 2 servos are going to rotate in a strictly ordered sequence. And here's the code. I'm right here. This is the code to rotate the servo 1 time. So to move servo 1 time, we're going to use this code, and it says that if servo 1 moving is false, and servo 1 moving is currently false because nothing has moved yet, then we're going to set servo 1 to position 1, and we're going to set servo 1 moving to true because now the servo has started moving, and then it'll automatically break out of this loop for if servo 1 is not moving because now it's true, not false. Then we're going to calculate something called servo 1 done time, which is the amount of time that it takes to execute these lines of code and send the message to the robot, hey, you need to move to servo 1. And then this 2.5 seconds is there because that's how much time I estimated would take servo 1 to rotate into position. And this is, so overall, the servo 1 done time is how much time it should take to execute the code and make sure servo 1 is in position. And next we're gonna move servo 2 into position. And we're gonna do that using another if statement. So if servo 1 is moving and servo 2 moving is false, which is how it should be right now, then the runtime, we're gonna wait until the runtime is greater than or equal to the servo 1 done time. If you remember from earlier, servo 1 done time was how much time we know it will take servo 1 to move into position. And we're gonna wait until that much time has passed before telling servo 2, you're safe to go because servo 1 has already finished rotating. And then we can move servo 2 into position 1, and then we can set servo 2 moving to true. Now I'm going to explain the state machine from earlier in further detail. State 1 for the second demo would be no servos moving, and trigger event 1 would be pressing the play button, and that will transition it into state 2, which is servo 1 moving, and then trigger event 2, elapsed time. That's basically we're making sure that servo 1 is in position because we estimated how much time it would take to get into position. Once we're sure that enough time has passed that servo 1 is in position, we can move servo 2 to position, and state 3 would be servo 1 moved, servo 2 moving. In an actual FTC match, the driver would use a video game console to press a button, and the trigger event 1 from no servos moving to servo 1 moving would be a key press. So they would press one of these keys and it would trigger that. However, in my demo, I just used the phone because I didn't have the gamepad, and I just wanted to clarify that because in a usual FTC match, we would use a gamepad and a key press would be the first trigger event. And the credits go to my mentoring team, mentors, my parents for always answering my questions, and Coach Gu and Coach Fong for helping me troubleshoot my code. Okay, does anybody have any questions? You can send them in the chat, and I'll be happy to answer them. Okay, so it looks like Scott asked, is your software posted online somewhere? Yes, if you're talking about what website I use to program, is that what you mean by software? This is just the, I don't think I have a picture. It's called the First Robot. Hang on. It's an official First website that I use to code. And it's connected to the control hub Wi-Fi. So I think you'll need one of the control hubs from Rev in order to access this website.
Yeah,
But
I'll take that, Evelyn. I think Scott was asking, he or she is basically, I think he's basically asking if he can get your code shared somewhere. So we can post the sample code in the GitHub later.
oh yeah, I can put this code, sorry.
Yep.
And this, I'm pretty sure my presentation will also, the slides will also be emailed later. Or you can find this, I don't know.
Yeah, probably gonna be a GitHub link.
Okay, then I'll post it there.
All right, thanks, Evelyn, for that presentation. Our next presenter is also from Team 18227, Matthew Bybee, and he's going to do a presentation about TensorFlow and Vuforia with OnBot Java. Matthew?
Okay. So I'm on. Oh my God, got it. About me, I'm Matthew Bybee. I'm an FTC rookie, and I'm a programmer on the FTC ACP Area 52 team. I go to St. Mark's as an 8th grader. So today I'll be talking about what is TensorFlow and how to use TensorFlow to detect minerals and skystones, and Vuforia object detection and positioning, and view marks. Oh, I guess we have to spike. So what is TensorFlow? TensorFlow is an end-to-end open source platform for machine learning. It has comprehensive, flexible ecosystem of tools, libraries, and community resources that lets researchers push state-of-the-art machine learning and developers easily build and deploy machine learning-powered applications. The FTC Software Developer Kit includes a light version of TensorFlow, which is tailored for cell phone and control hub processors. Also, it contains lots of pre-trained models for each season. The models are used to identify the skystones or the cube and the ball that are included as data files that can be loaded by Java codes. The computer visions options in FTC are TensorFlow, Vuforia, and OpenCV, which isn't available for OnBot Java, and TensorFlow and Vuforia are the officially endorsed options by FTC. So how to initialize TensorFlow? To initialize the camera, you use the Vuforia localization engine.
Note that Vuforia is different from TensorFlow. You see Vuforia in your code lines, but it's only used to activate the camera. So TFOD is TensorFlow object detection, and to load the models, you have to use TFOD model assets. How to use it. To use a model, you put all of it in a while loop, so it continually checks over and over again. So to use it in Rover Ruckus, you can use it to recognize the minerals and also provide the model pixel information in the camera resolution if it's relatively to the right, center, or left. So TensorFlow in the Skystone season, you can use it to separate the Skystones from the regular stones if they're at least 1 inch apart. So TensorFlow was reduced in season 2018 with a very successful recognition rate, but it fully relies on the pre-trained models in the software developer kit. In 2019, the situation is that it has decent successful rate with recognition when 2 stones are well separated. So when bricks are connected, it only sees one object. I don't have the example here, but it looks as if this red box would just be around both of the bricks and not one box for each brick. To help solve this, FTC is developing a system for teams to train their models. Vuforia, how it works. It uses the Vuforia AR software developer library. The images from the robot controller camera are compared to the library images for different features in multiple dimensions, where you can also define transformation of the images, such as rotation, stretching, or movement. Then you can use Vuforia's API to find out where the item is relative to your robot. Vuforia's main limitation is that it only works consistently at a distance of under 2 feet. So how to initialize Vuforia? You initialize the Vuforia parameters, as you can see here, and you load the model just with this one thing. With this, there are 13 targets, of which the actual Skystone is the first. Simplifying the task. You can use all of those models, which are this bridge, but all 3 of these bridges and these pictures around the wall. So this is how to use it for the localization. You see here, it says set location, and you take the X, Y, and Z, and you rotate them in the robot's perspective so you can see it correctly. 90 degrees along the X-axis. So this is calculating the relative location to the target. This part is if it doesn't see anything, it just keeps on going through this until it does see something. Then it goes through this once it does see something. These are relative locations of Skystones to robot. This is the center, and these are 2 other different angles, such as from the side. From each of these, on your driver station app on your phone, it will show different readings for the X value of your camera relative to the Skystone, or the X and Y values. Viewmarks works by looking at a set of photographs which are set as anchors with minor variations captured in the camera, such as these. The robot relative position to the anchor picture is deduced, which is then used along with anchor picture location to calculate robot position on the field through a matrix transformation. So this is Viewmarks for absolute field position, and this is the Skystone site. And these gray things are the 8 pictures. So this one's rear 2, this one's front 1, front 2, rear 1. And then blue 1, blue 2, red 1, red 2. This is the utilization in Rover Ruckus, which is from 1 year earlier. And there are only 5 in this one. So my thanks are to my mentoring team, which is the 8565 Technic Bots, my mentor, Anthony W., and parents and coaches for helping whenever I need it. Does anybody have any questions? Okay, so does nobody
All right,
have
if there are no questions, then we'll take a break until 2:55. That's a 10-minute break, where we will resume our list of presentations. You can use this time to fill out your fill out your proper name to be entered in the raffle, or you can also take some time to fill out the survey. Fill out a survey, which is I will post the link to that survey in the chat. So again, we'll take a short 10-minute break and we'll resume at 2:55. All right, we're going to resume our list of presentations. And again, please take some time to fill out that feedback survey. It'll be really appreciated. And just another reminder, we will start taking attendance for the raffle drawing 10 minutes before the giveaway, which will be at 3:55. So without further ado, let's start the next presentation, which will be presented by Matthew Lee of FTC 18227, and he'll be talking about FTC dashboard. So, Matthew?
Okay, hi. So today I'll be talking about the FTC dashboard. And just a little bit about myself. My name is Matthew Lee, of course, and I'm a programmer, and I'm also a sophomore at Jasper High School. So today we'll just be going over what the dashboard is, how to build the dashboard, how to add features to it, and how to use it. So first off, what is the FTC dashboard? Well, it's a customizable web dashboard, which is based on the language Java, and it allows for your team to do efficient designing, testing, and tuning of the robot. And one of the ways that can happen is through configuration variables, which are basically just variables that you can change them while the op modes are still running, instead of having to go back, change your code, and rebuild it and re-download it. The dashboard's code is designable to be accessible and expandable, which means you can add to it and also take away from it. Some features of the dashboard include the live telemetry graphing display and the just live telemetry data, and also the real-time configuration variables and a camera view. The dashboard is developed and maintained by Acme Robotics, which means that you cannot build onBot Java into the dashboard. So yeah, and you can also start the op mode from the dashboard without having to use your phone. So to build the dashboard, the first thing you want to do is download and install Git. And what this does is it will allow you to clone the dashboard source code from GitHub later into Android Studio. And yeah, next you're going to want to download and install Android Studio. And inside Android Studio, you're going to want to download and install Android SDK Platform 28. And next, you clone the files from the source code right here into Android Studio. And then you connect to Control Hub through the Wi-Fi and follow instructions from this link to set up your computer for ADB connection, which is wireless. And basically what ADB connection is it allows you to essentially just download and run the code and like basically build it into your robot. So to do this, you're going to want to open the command prompt and type ADB connect 192.168.143.1, and this is just for the control hub. So yeah, and then you press build and then make a project and run it. So some of the features, like I said earlier, are live telemetry, data, and graphing, and configuration variables, and also a camera view. So for the live telemetry data, how to implement it into the dashboard, you can use two methods. The first method is called SDK telemetry, and this is just a simple method which uses the get telemetry command. And the second one, which is the preferred way, is called telemetry packets, which basically creates a packet which you can put the data inside, and it will display on the dashboard. The reason packets are preferred is because not only can packets be used for things such as telemetry, but other features on the dashboard, such as a custom field overlay. You will then use the add telemetry to add whatever values that you want to be displayed. And then the added telemetry will automatically be put on the graph. So next are configuration variables, and these are basically just variables that can be changed while the robot is still running. And this, like I said earlier, allows for extremely efficient testing and tuning of your robot because you don't have to go back and re-download and rebuild the code. So the first thing to implement this is to declare the variables that you want to be configuration variables at the beginning of the code inside the class. And then you want to type the @config annotation outside of the class. And you want to, and basically now, after you've implemented these, like I just said, rebuilding and downloading the code is now unneeded. And to change the configuration variable inside the dashboard while your op mode is still running, you want to go into the section in the dashboard called configuration variables and select the op mode and value that you want to change. And once you change it, you have to press enter to save it, or else it won't be implemented. So these configuration variables, they won't go back to their default value that you set for them until you actually restart your robot. So yeah. The camera is next, and to implement the camera into the dashboard, you want to take the webcam and plug it into either port USB 2.0 or port USB 3.0 on your control hub. After plugging your camera in, a new op mode should appear in Android Studio, which has the camera's code in it. And you want to change the place where it says final public static string Vuforia license key and set its value to your own Vuforia license key. And this can be obtained through the Vuforia website. So now for a live demo. So first of all, actually to get to the dashboard, you want to type in this right here, which is for a control hub, and then do /dash. That'll bring you to the dashboard. And yeah, so I'll be demoing this gyro turn first, and basically it will turn the robot 90 degrees, and you'll see on the camera here. And I'll also be showing the telemetry data and the graphing. So if I start this right here, you'll see that the robot turns 90 degrees. Right here, this is the degrees amount, and basically it will change like while your op mode is running. So, and I also magnified the correction value by 100 because it would have been too small to see on the graph. So I'll show you on the graph now what it looks like. So yeah, as you can see, this is the correction, and this is the heading right here. And you can also even change the window size. Basically, this changes the time and how fast or slow like it passes. So if I change it to 20,000, for example, as you can see, it'll go a lot slower. So yeah. And for this, I put some configuration variables here because these are variables that need to be tested very often, and now with this dashboard you can change it basically really easily. And yeah, so now I'll be showcasing this drive mode. It's a teleop, and I'll just be showcasing the configuration variables in here. So I'll just put the gamepad next to the robot to show it. Alright, so basically this right here is the servo, and I marked it with a yellow piece of tape so that you can see how much the servo turns. So right now, this is the servo position. It's set to 0.5, meaning it will only turn about 90 degrees. So yeah, I'll show you. I need to connect the gamepad first. Okay. Okay. So as you can see, it only turns about 90 degrees. And if I change the servo position to, let's say 1, and I'm going to press enter to save it, it should turn a little bit more to about 270 degrees. So yeah, that's the configuration variables, and to show you, I can show you the graph as well. So if I move the servo, it'll show the graph. If I move the robot, then that will also show on the graph, as you can see. So yeah. And just for earlier, I can show you guys the so what the ADB connection will look like. So after you do this, it should say, oh, hey,
ADB connect.
yeah, sorry, I did the wrong command. It's ADB connect 192.168. So as you can see, it'll say connected, and right here on Android Studio, now it says that it's connected to Rev Robotics Control Hub. So yeah, now you can download code into your robot. So that's it. Oh, and also, obviously, credits go to my mentoring team, which is FTC A565 Technic Bots, and my mentors, Byron Lee and Anthony Wong, and the parents and the coaches. So any questions? If there's no questions, then I think I'll stop sharing.
All right, thank you, Matthew, for that presentation. And our next presenter will be David Hu of Team 18227, and he will be giving an introduction on the prototype system. David?
Okay, hello everybody. My name is David Hu. I'm a part of FTC Team 18227 ACP Area 52, and today I will be talking about prototype. So here's a little bit about me. I'm a FTC rookie. I build and I also code a little bit. This year I'm going to be a 7th grader at St. Mark's School of Texas, and I've had 2 years in FLO. So today we're going to go over what is prototype, why do we need it, a little bit how to, and what's been prototyped so far. So the prototype system was developed by FRC Team Spectrum 3847. Prototype basically means prototyping with PVC pipe. You use 3D printed connectors along with your pipes to make a model of basically what you want to do. The holes, there's you can use different size holes, PVC pipe, and yeah. So here are some examples of some things that's been prototyped by the FRC team. You have like a bumper intake, you have a frisbee shooter, and also like a shooter and adjustable hood. As you can see, they all use like the pipes, and you basically can make a model without actually have to build it. So why do you use prototype? So PVC pipe is easy to get. You can get around 10 feet for around $2 at Home Depot. The goals that the team had in mind when making prototype was to make it cheap, easy to add and remove parts, make it have unique allow like unique parts, and also allow you to use like hand drills to power it instead of attaching motors and programming everything. So a little bit of how to. So in this file, in this link, you can find many like these different connectors to help you. Like basically, you can 3D print them to help you build your prototype. Personally, one of my favorites is this drill mount. You can attach it onto the end of the pipe with us, and then you can attach a drill onto it to spin the pipe. So some tools you might need for prototype, you're going to need a 3D printer, either PDG, nylon, or polycarbonate filament works. You need like a CNC router to make sheet parts, and also some drills and PVC cutter. So this year they added many different PVC, many different like clamps and mounts and connectors, and also they added the drill adapter. Basically, with one of these hex shanks, if you fit it into the like the right size, you can like clamp your drill down onto these. Our team uses the 3/8 inch. So prototyping for FTC robots. So for FTC, there's many different types of intake systems. We're going to be focusing mainly on the noodle sweeper style. So for the noodle sweeper, our goal was to test how effective prototype system was. See like the different materials to test, and the materials we tested are like surgical tubes, zip ties, and spear gun rubber. So here is a prototype of what I've made. You see all the connectors. Basically, this is like the sweeper, and we have like the frame with all the 3D printed parts. So what has been done so far? So this is my robot frame. Austin, my mentor, helped me 3D print these parts and assemble the frame. And then I made like a box and a ramp out of a box, and to lead the stuff that's been swept in into a box at the end. So here's a demo. So right here is the part where you attach the drill. As you can see, like when I spin it, I can easily sweep in the box, and I added this back part so it doesn't spin off because the drill is powered really fast. So some observations I had when making this was that the noodle sweeper is pretty efficient for intake. The prototype system was pretty efficient, and but one of the drawbacks was that the hand drill kind of spins really fast. So if you swept the stuff in too fast, it would like fly off the ramp and hit something else that you didn't want it to. Some future materials I hope to work with are like zip ties, some like springs, and rubber and zip ties combined together. So I'd like to give credits to the FRC team Spectrum 3847 and the mentoring team FTC 8565 Technical and my mentor Austin. Is there any questions? Okay, I guess I'll stop.
All right, if there are no questions for David, then we'll move on. Our next presenter will be Nate of team 13811, and he will be talking about odometry wheels. Nate? Okay, I think Nate is a little bit late. So we're gonna move on for now. Our next presenter, who is supposed to be after Nate, is Mr. Patrick Maycott of Team 7172, and he is going to give a presentation about Rev build models. Mr. Maycott.
Hey, everybody.
Victor, I saw there's one person called it 13811 presentation of encoders. Is that the person? Let me allow to talk to see.
No, he's not talking about encoders. He was going to talk about odometry wheels.
It might be the same because that's the presentation team 13811. Odometry wheel is also, he's talking about replacing the motor encoder with odometry wheel.
Yeah, I think that's the one.
I allow them to talk. Can we, is that the right person?
Hello? Can you hear me?
We hear you.
Perfect. Can you see me?
Okay.
I see that you're presenting. I don't see you yet.
I'm going to promote you to a panelist.
Hi. So, I'm Nate Michaelis. I'm captain of 13811. I've been captain for 3 years, and this is the 3rd year of the team. And this is our competition robot for this year. And I'll have Andrew Miller present the physical aspect of it. Here, close it up.
Hi, I'm Andrew Miller, and I'm an engineer on the team 13811. I'll be going over the design of the encoders and all that. So last year we wanted to try to stand out as a team by making the robot really compact, but that didn't really end up working out. So we wanted something that would end up being much greater than that. So to do that, what we did was we added a nice encoder system on the bot, but that took a whole lot of trial and error to actually get it right. So last year when we tried to design the robot, I mean, we were all really inexperienced. There was a whole bunch of new people on our team. So when we actually designed it, we didn't think about autonomous at all. We just kind of put a drivetrain on there and an intake mechanism. So we ended up just having enough room for an encoder system. And when we actually put it on there, it was just kind of slapped on. So this year, we actually have a dedicated encoder mount. And the encoders are all pretty much the same design as last year. But to actually get to that design, there's a whole lot of trial and error. So at first we had some really cheap encoders that we ran for a little bit and they just kind of broke down. And then we had some larger ones that were nicer ones, but they just didn't fit in the middle of the robot. And after that, we had some ones that were also nice and they fit in the robot, but they didn't work out for programming. And so that's how we ended up with the ones that you see here today. They worked well with the robot overall. Anyway, the design for the encoders this year is pretty much the same. There's some slight modifications, but you can see here, this whole mount is dedicated to just the encoders. Last year, one of the problems we had with the encoders was the height, which was probably the biggest issue. Because if you have the encoders too high, they won't track. These wheels won't touch the ground, it just won't track. If you have it too low, then it can actually bend this axle and break the encoders, which is obviously a huge problem. So we needed a way to get it set at just the right height. In order to do that, we set up these RC shocks. So that way, when you set the encoders down, it pushes against the ground. And it can go on any surface and just be at just the right level to track. Another problem was that we have two wheels here. Last year we only had one, so sometimes it wouldn't be touching the ground and the wheels would just kind of slide along the ground and not track. And the final problem was these wires. These wires aren't rev compatible, so we needed a way to transfer that over to rev compatible encoder wires. So we just ran it to this soldering box right here and then ran that out through this plexiglass up at the top and just ran it to the expansion hubs. So anyway, that's pretty much all of the engineering aspect of the encoders. So now here's Jacob.
Oh, okay. I'll get the robot out of the way. So I am Jacob Newland, and I'm the head programmer on our team. And I will be showing you the code part of how the code, the code is used with encoders. I'm going to probably try to screen share my GitHub repository so I can figure out how the mouse works in this computer. Okay. Okay, we got it. I think.
You are.
Okay, you guys see it? Okay, hope it's seen. So, as you can see, we have a GitHub repository for all of our code. It's just FTC 2020, 13, and 11. If you ever need to look at it, you can. Because I'll be showing you how it works in the autonomous. So, as long as you skip all the import stuff, as you can see, oh, hang on, just making sure I'm talking to the microphone. So, throughout all the imports and stuff like that and the IMU setup, the thing I think that's pretty cool about our code this year is, or last year actually, we used this last year, was that we use this like function-based move mechanism thing, such as like the first move is move forwards, and there's a whole bunch of what looks like arbitrary numbers. But in reality, you're moving direction, which you're moving forward on this case. Pulse, you're moving forwards, 4,250 pulses at 0.5 power. And that 10 right there is a timeout variable. If it reaches past 10 seconds to take its move, it'll just cut it off. So the timeout variable and the pulses were all we actually used last year for our, like all of our ways of finding where we were on the field and stuff. So as you can see right here in this nasty bit of a while statement, there is in pulses in crane extend, we had to actually use one of our crane extension motors for to spare encoder port. And if you see that just makes sure it's timing out. So, well, as you can see, all the pulses, if everything lines up, it stops when it's supposed to, and it just keeps on going. Or it doesn't keep it going. Of course, it keeps it going through the rest of the autonomous. At the end of every single of these moves, it goes on to the next one. There's a strafe command, which unfortunately won't work because our our robot currently is missing the correct amount of wheels or the correct wheel. But this is our code we used last year. And I would like to show you guys the precision that we get even with our nice Omni wheels. Wait. So actually, hang on. I do want to address something right quick. So I just want to show the importance of the timeout variable. Last year, our encoders weren't actually they were the same thing, but they weren't actually like, you know, sorry, I'm trying to think. They weren't actually very durable, or not durable. They weren't very precise. I mean, they kept on like getting skipped and stuff, and they weren't doubled up, so they would constantly like slip and stuff. We basically had a completely timer operated robot. So this year, well, in this test, I moved the timer up to 10, which is way longer than any move should take. And I'll try to operate the webcam to where I can show you the robot moving, okay? Okay, I'm sorry, just bear with me for a second. Stop sharing the screen. And I'm gonna get the robot set up real quick.
So, well, while they're setting it up on the field, we decided to not use the Bohr encoders, which we have, as well as using what Andrew said earlier, just like the motor encoders itself, is because every single direction change adds slippage. And using the encoders and none of like the motors for like response using pulses, what we're about to show you can give you a precise autonomous run every single time with barely like any centimeters of slippage at all. You good to go, Jacob?
Just a second.
Okay.
Oh yeah. Okay, so
ready to go?
I have set up a piece of red tape where the robot wheels are located, and I'm just gonna let go, I guess. So as you can see, it landed up pretty much center.
Yes.
Of course, some changes need to be made because the wheels kind of suck right now, but it's a work in progress, and I think we're doing pretty good.
So 13811, thanks you for watching our presentation, and if you need anything, just contact the Aledo robotics team. We have web pages just on the Aledo ISD school site. We also have our own Instagram at 1311 high voltage, and we have our own email 1311 high voltage. So if you have any questions, tips, concerns, anything, just feel free to reach out. Other than that, any questions? Any questions at all?
There are questions in chat window. Victor, can you read out?
Perfect.
Okay. Question from Scott. Did you try to use the encoders on your drivetrain motors?
Yes. Jacob, do you want to explain using the motors?
Okay, so we did try that. We honestly, I think we did. Everyone else did. We tried it out there first, but it got a little bit strange with all like motor modes and stuff. Where we decided that, well, not that, it was just kind of inaccurate. We couldn't get consistent results every single time, and although it's autonomous, nothing's going to be consistent every time. It just didn't get it every single time, or not. Sorry, that was a bad way of putting it, but it just wasn't as precise as we wanted it to be.
Then the next.
All right, we have our next question is, you have a unique frame. What is it built out of?
So if you want to get the computer Andrew and demonstrate on the robot, we decided to make this robot. We named the modular chassis. 90% of this robot is either made out of 3D printed parts like the corner brackets, where we can easily take off the whole top and bottom of the robot using screws. And we just unscrew 8 of these and we can pull off the top. The next, we used PVC, which we're gonna soon use shocks, RC shocks, to make it a live axle, as well as, so just like our own encoder mounts and our encoder wheels. And the rest of it is made out of inch-thick plexiglass and door slides and the Rev black ionized extrusion. Make it super modular, easy to wire up, and looking very, very clean. Any other questions?
I don't see any more questions in the chat. The question about the corner brackets was already answered. So I'm assuming there are no more questions.
Victor, watch the Q&A window. There is another open question from Maddie.
All right. Right, from Maddie, if you could change the kind of wheels you use, what kind would you use?
We were buying Go Builda wheels, but they ran out of stock. What we previously had were the Rev Mecanum wheels, but their diameter and circumference was way too small to the point where, if you can see, we easily just add, like, just slide it onto the axle. Hold on. You can see how we do not have, you can see the difference, like the size. They just wouldn't work with the PVC and the 3D printed parts. So we're going with the Go Builda wheels soon.
All right. So I think that's all the questions now. I don't see any more questions in the Q&A or the chat. So thank you, Team 13811, for that very interesting presentation. And before we move on to the last presentation, I would like all of you to take some time to fill out our feedback survey. We heavily rely on the feedback, so we would like everyone to fill out this quick survey, and I'll post the link in the chat right now. Okay, and our final presentation will be given by Mr. Patrick Rickard of Team 7172, and he will talk about Rev build models. And just a reminder, we'll start taking attendance for the giveaway number 3 very soon. So just be aware of that. And now, Mr. Patrick, the floor is yours.
Okay, so good afternoon, everybody. Thanks for attending another session. I'm really looking forward to this one. I've been looking forward to this one for some time. Hopefully you're able to see my screen okay and hear me okay. If not, somebody say something in the chat window or in the panelist window and let me know what's going on. So my topic for today is, it's about Rev parts and Rev chassis, but it's I'm relabeling it a little bit about 7172 drivetrain concepts, and I'll give a little example of why I'm calling that. So the drivetrain, of course, is the part of your robot that gets it from one place to another. And 7172 over our past couple of seasons has come up with a really nice drivetrain. It's worked well for us. We started it with the Rover Ruckus season, which you can see in the video down on the bottom left. And the 7172 robot is the one right there in the frame right now. And you can see that it's pretty speedy, it's quick, it's able to get around, and that's what you really need if you want to be able to compete at high levels. Is your robot needs to be good, and you really want it to be fast and maneuverable. That drivetrain was so good that we used the same one for the next season. We basically used the same one with just a few very small modifications, and that's the video that's up in the upper right-hand corner of the thing is our robot competing this last year. And again, you can see it's pretty speedy and it's able to move around pretty quickly and so forth. So we're really happy with that. The team members who made a lot of that robot have graduated. This was their last year, and we have a new team. We have some continuing team members, but we're also getting a lot of new team members. And I've also had a personal goal to kind of show people the drivetrain possibilities, especially using mechanism wheels. Many of you know that I've taught courses in the summer and in the fall, and one of the things I'm constantly asked is, how do I use a mechanism drive? How do I create a mechanism drive? And so I set for myself a challenge of trying to create a mechanism drive based robot made almost entirely from Rev Robotics parts. The robots that you saw in the video there's a lot of custom parts on it. And so I asked myself, what can I do now that Rev has mechanism wheels? What can I do to make a robot that's almost entirely out of Rev Robotics parts? And if it does have any custom parts, they need to either be easily available or they need to be something that could be 3D printed and still have a reasonably good chassis. So what I came up with is this, and I'm calling it a 7172 style drivetrain, but Rev based, made almost entirely out of Rev Robotics parts. The CAD model for it is on the left, and for some of the coaches and others who have been attending my chat clinics on Thursday evenings, then we've walked through some of the steps of designing this robot in Fusion 360. And I've gone ahead and built the robot, and you see that in the picture on the right, and I'll show a video of how it works here on the left. But again, the key feature of this robot is that it's almost entirely Rev-based. So let me go ahead and start that video real quick, as soon as I get my hands on the right keys here. So here's the robot. It's just driving on a field. You can see it's pretty speedy. It seems to go reasonably quickly. And is able to zip around. It can go sideways, it can go forward and backwards. Going fast is something that the 7172 team has been really, always has been important to them. And so I wanted to try and duplicate that as well. One of the interesting parts about making that particular robot is what I discovered was there was some design principles that were embedded in what the team had previously designed, and I wanted to pull those out. And so that's really the topic of my talk today, is what are some of the design principles behind that style of drivetrain and robot that made it successful for 7172. And so that's what my talk is going to focus on today, and cover a few different things and that people might want to look for or consider when they're designing a chassis, and especially if they're designing a mechanism-based chassis for their competitions. So I should note before I go too much farther that Rev Robotics just a few weeks ago released their own plans for a mechanism-based drivetrain, and they're fine. And you can get them from this address, or if you go to the new Rev Robotics documentation site, then it's not hard to find. I just did a search for mechanism and it came right up. But they now, with their new starter kits that come with a lot of the channel pieces, are able to give teams a design for a mechanism drivetrain. And I sent my plans and my video that I just showed you to some of the technical folks at Rev Robotics and said, hey, what do you think? And they said, here's ours. What do you think? And we've been kind of exchanging ideas back and forth, and I'll share some of those with it. And as I was looking at their design and comparing it to the 7172 style design, that's when I knew I really wanted to make a presentation like this one to cover what the different pieces are. So this is just a list. We're going to go through each of the items on this list with some slides and some demos. But the key concepts behind the 7172 drivetrains over the last couple of seasons are, one, that they've been mechanism wheels, avoid using direct drive, that is, avoid attaching motors directly to the wheels, use chains for transmissions, put the chains on the outside of the wheels, Use dead axles, attach the sprockets and the bearings directly to the wheels, and be sure and take care of ground clearance. So I'll go through each of those in a little bit more detail for the rest of the presentation. I do also want to note that this is just one of many possible designs. There is no way that I'm saying that this is the design that every team should use, or even that it's the best design. It's just one that worked for 71, 72 over the past couple of years. They actually came up with the foundations for it after the after the Relic recovery season in the off season, when they recognized that the drivetrain they had previously just really wasn't performant enough. And just to get a comparison of the Rev Robotics version of the Mecanum drivetrain and mine, the one that I came up with, you can see that there are some differences. And as I go through and describe the parts here, you can refer back to the Rev Mecanum design, and you can see how I kind of like some of the features that my design has over what the Rev Robotics design has. All right, so the first thing is to have Mecanum wheels. If you're a rookie team, you probably don't know what a Mecanum wheel is, and yet there have been a lot of presentations where they refer to Mecanum wheels. A Mecanum wheel is a special kind of wheel. And it's a wheel, but it has rollers on it set at a 45-degree angle. And when you get 4 of these on a robot, what it enables your robot to do is to go forward and backwards and turns like normal wheels would allow you to do, but it also gives your robot the ability to strafe, to move sideways. And so in the last 4 seasons, certainly going back up until Rescue was not a good game for robots with Mecanum wheels, but the last 4 seasons, if you had a robot that was fast and was Mecanum based and had some strength to it, then you generally had an advantage over those robots that didn't. So Mecanum was important. Oops, let me go back a slide. The 3 places to get Mecanum wheels these days that I would consider is Rev Robotics with the 75mm wheel. And as High Voltage just recognized, it's a smaller wheel, so you have to design for that and take that into account. GoBuilda came out with a set of Mecanum wheels last year that are widely considered to be pretty good. The longtime standard in First Tech Challenge has been the Nexus wheels that are available from robotshop.com. One of the things that was important to the robots that we've done is to avoid using what we call a direct drive system. So a direct drive system is where the motors are directly attached to the wheels. The last robot that we had that was direct drive was from the rescue season, and it tore up the gear boxes on our motors. We were literally replacing motors at least before every event, and often in the middle of an event. And that's not something you want to be doing in the middle of a competition or in the middle of doing alliance playoffs. So so since then, we switched to doing chain-based drives, and I'll talk a bit about that. There's a couple of reasons for not wanting to use direct drive. So one of them is that it's bad and hard on your motors. Another one is that it's hard to get the wheels straight, but also it tends to encroach, because the motors are directly attached to the wheels, it tends to encroach on space where you'd really like to have an intake. For most fast designs, and certainly the ones that were in the videos that I started with, you want to be able to have your game elements come in on one side and be scored on the other. You want them to pass through the middle of the robot. And with if you have those motors in the front right there by the ground driving the front wheels, they get in the way. It makes it much harder to be able to collect game elements off the floor and then bring them into the robot and be able to do things with them. So we wanted to get rid of the direct drive for that reason. Another thing that we have settled upon is that we tend to always use chain for our drive transmission. That is how we transmit power from the motors to the wheels. Once you've decided to not use direct drive, your basic choices are gears or belts or chain. We've done all of them. And We've kind of settled on chain because it's really robust and reliable, and it's very forgiving. And what I mean by that is that you don't have to have things super precisely spaced, or if things get just a tiny bit out of whack, it doesn't fail entirely. You're still going to be able to move around and move pretty precisely. So that's worked for us. It's also easy to make adjustments. If you're using gears for your transmission, then it's hard to make adjustments because you have to change the gears. You have to change the spacing. You have to redesign your plates and your mounts to do that. Same thing for belts. Belts are easy to move around a bit, but if you can't easily just cut a belt and splice it back together and have it work well. You need to be able to have belts that are exactly the size you want. But with chains, it's easy to cut them apart, splice them back together, and get exactly the size chain you want, so you can try different things and move them around. It's also very easy to change your gear ratios when you're using chains. You can just change the size of the sprockets and be able to get different gear ratios to your wheels. Over the last couple of seasons, 71-72 has ended up with an effective gear ratio at the wheels of 16-1. In other words, they're moving at the same speed as they would if you had a 16-1 gearbox on a Rev Robotics motor. And that seems to be pretty fast and still have enough torque that the robot can move around efficiently. The other thing that I discovered while building the Rev Robotics robot that I think is an important concept is that the chain needs to go on the outside of the wheels. One of our robots had the chain on the inside of the wheels. And what happens if you put the chain on the outside of the wheels is that moves the motors out of the middle of the robot. They go off to the sides behind the wheels. And you can see in the pictures that I have in this slide that in the first robot design where the chains are connected to the inside of the wheels, then the motors are right there in the middle of the robot where you'd probably like to be able to do some game element processing. But if you just switch it so that the chains are on the outside part, then the motors tuck in behind the wheels. And on the third one, which is the drivetrain chassis that was used for the Skystone robot this past season, you can see the motors aren't interfering in the middle of the robot at all. They're completely tucked away. And so now that whole center section is available for game elements to come in and be scored and processed, which is part of what made 71-72's robot pretty quick this last season. Another important feature, and this is something that I worked with Rev Robotics to kind of come up with an answer to, is the ability to use a dead axle. So a dead axle is one where the axle itself doesn't spin. For most robots that you build in any of the building environments, they typically have a motor is driving an axle that is attached to a hub or something like that. And when the motor spins, the axle spins, and then the axle's connected to a wheel or a gear or something that makes the wheel actually turn and move around. And 71-72, when they first started this design, they used live axles, and they had a problem that the bearings would often pop out of the brackets. So I have kind of an example of that here. So this is a Rev Robotics design with the end of the place where an axle would go. And these are the indexable motion brackets. And in fact, when I first sent my CAD model to Rev, they came back and they said, you do know that the indexable motion brackets tend to bend a lot, right? And I said, yes. And I'm just going to show that on this video here. If you pull them apart, you can see I'm not pushing very hard at all, but they can bend inward and they can bend outward. So if there is a shaft in there that has bearings, I don't have one handy, but if there's a shaft in there and it has bearings on it, and the brackets move while you're busy doing that, then it's really easy for the shaft to come off the bearings or for things to slip. And so that doesn't work very well. So what we tried on our Rover Ruckus robot was we said, what if we did dead axles? So a dead axle is the same thing, but here we don't expect the axle to move. We mount it directly to the brackets and it doesn't spin at all. So here's a pair of locking motion hubs from Rev. This is a new product this last year, and they're attached to this axle and it is fixed in place. And when you have that, the plastic brackets become much more stable, much stronger. So now I'm going to push on this with both hands to try and bend it. And you can see it doesn't want to bend much at all. And it certainly doesn't deform the axle, and the axle has no chance of slipping or coming loose. So the dead axles just all of a sudden our drivetrain chassis just became really solid and straightforward, and that was a nice thing to have. So I really like having the dead axles on the robots. But if you're going to do that, now instead of the axle holding the bearings and spinning, the wheels have to do that. The wheels have to spin around the axle. And so 7172, the robot designers were given the task of coming up with a way of attaching a sprocket directly to the mechanism wheel. So not a sprocket attached to an axle to the wheel, but attaching the sprocket directly to the wheel. And the right-hand photo of this slide shows the thing they came up with for the Nexus wheels. They created a custom plate, and that plate would then attach to the wheel, and then the sprocket had a spacer underneath it, and it would attach to the custom plate. And inside of that, you can't see it in this photo, but on either side of the wheel, there's a pair of bearings that are there. I wanted to do the same thing with the Rev Robotics wheels, but the challenge is that the Rev Robotics wheels don't have flat plates on the side that you can easily attach things to. It's inset. So I asked Rev how they would do a dead axle sort of design using the Rev mechanism wheels. And after a couple of rounds of emails back and forth, we finally decided that pretty much you're going to have to go with a 3D printed piece. There's not a set of pieces you could buy off the shelf that would do the job. So this is what I came up with. It's a 3D printed piece that goes in the middle here. It has bearings inside of it. Do I have my other one here? Yes. Here's one with just the 3D printed piece. And inside the 3D printed piece are a pair of bearings that have been embedded into the piece. That are ball bearings. They're really stable, and then they have the Rev hex pattern inserts that go inside of those bearings, so it can take a shaft. And so you use that with your Rev wheel, and I'm just going to go ahead and put it on this shaft real quick. Actually, I'm going to use the longer shaft here, so that you can see how well it spins. If I can get it in here now, let me try it from the other side. There we go. There we go. All right, so here's the Rev wheel. Now I'm holding the axle, so the axle's not spinning. And if I spin this wheel, you can see that it likes to spin for a good long time. It's really smooth. It's got great motion for being able to keep working. So that was the next piece, is to come up with a way to attach the sprocket directly to the shaft. One thing I will say is that when you do that, you don't want to put the load of turning the wheel on the 3D printed piece. So this sprocket is attached to this wheel, but the screws that are here are going all the way through the 3D printed piece to nuts on the other side of the wheel. So it's not that the sprocket is turning the 3D printed piece, which turns the wheel. The sprocket is turning these long screws, which then turn the wheel, and the 3D printed piece is just sandwiched between them. The last thing that is important to 7172 robots wasn't important so much in the Skystones series game, but was very important in Rover Ruckus, is to make sure you have good ground clearance. So ground clearance is the amount of room underneath the robot for things to happen. In the Rover Ruckus season, you wanted ground clearance for two reasons. First of all, there were craters on either side of the field in either corner. And if your robot tried to go over those craters or needed to go into the crater and out of the crater, a lot of teams would get caught on the crater ridge and their wheels wouldn't be touching the ground, and therefore they couldn't move anymore for the rest of the match. So high ground clearance is important for that. It's also important in debris-based games where there are lots of small pieces of game elements on the field. You want to have high ground clearance so that your robot can safely pass over them and not get stuck on them, or not end up bulldozing a bunch of them around the field where you might get penalties for controlling more than one object. So for Rescue, which was a debris-based game, and for Rover Ruckus, and for some other games, 7172 has learned to try to do high ground clearance just so that you can easily get over whatever obstacles or debris may happen to be on the field as part of the game design. That's a game-specific question. For Skystone, there were these very large bricks, and so there wasn't much chance of the robot rolling up over a brick, and so for that reason, they went with a bit of a lower ground clearance. In the Rover Ruckus ground clearance in the pictures that you see in this slide, the team made sure that there was at least 3 1/4 inches of ground clearance. And that's because the silver balls, or the balls that represented silver elements, were 3 inches tall. So we wanted to make sure that the robot could pass safely over those without getting caught on them or being in danger of treating them as controlled elements. But the Rev robotics design that I came up with has a really low ground clearance. The motors are really, really low to the ground, like about 3/4 of an inch. And to me, when I did my video and did my test of the robot, I was like, wow, this is a really good robot, nice low center of gravity. But if the game is a debris-based game, it could pretty easily get hung up on those. And you would like to have a way to be able to get more ground clearance. The idea I have at the moment is to take the indexable motion brackets that I'm currently using in the design and replace those with some of these C channels that are a bit longer and they're very strong. So use a C channel, and what that would enable the design to do is to get the axle up farther away from these top rails, because the C channel could go down lower on the side and raise this up. So even though you have those little tiny Rev mechanism wheels, you'd still be able to get enough ground clearance for the motors and everything else like that. If you're able to separate your motors from the wheels so you're not doing direct drive with chain, then it becomes much easier to put the motors at a higher plane than where the robot wheels happen to be. So let's see. So those are the key concepts that I came up with just by taking the design that I used. And now what I'm going to do with those is I'm going to pass those along to the new team of designers that's coming up for 7172. It's going to be nice to be able to say, hey, these are kind of the features that I think made 7172's drivetrains work really well in the last couple of seasons. And so you might want to preserve that for the designs that you use in the upcoming season. There's a couple of questions that have come in. So let me answer those questions. So one of them is from an anonymous attendee asking if there are any cons for the mechanism wheels. And the answer is yes, there are. For anything where you need to climb something, if you need to climb a ramp or if you need to go over an obstacle, mechanism wheels aren't always the best. And so you want to be really careful about that in those kind of situations. Because the mechanism wheels have rollers, it's very easy for the when the robot's trying to make its way up a ramp or up an incline, it can start to roll on the rollers as it's doing that and maybe not get very much traction. So that is one potential downside for that. The other con that has often been stated for mechanism wheels, but we haven't experienced it, is that it's a robot with mechanism wheels could get pushed around by a robot that's not using mechanism wheels and has higher traction. And defense is the thing in First Tech Challenge where robots can push. You can't ram, but you can push each other around and push each other out of the way. And so knowing about, that mechanism wheels might give you a little less traction could be an issue. Any benefit to belt drive is a question from Wayne Dennis. So the major benefit that I would see with a belt drive is that it fits in a much smaller space. The challenge with a sprocket is the width of the chain. So when you have a chain going around this sprocket, and a chain also is limited in terms of its bend radius, how tightly it can bend. So by virtue of using chains, you know that you're going to have something of a reasonably high diameter for a low number of teeth. And and as you get more teeth, the diameter grows very, very big. So belt drive gives you better ability to fit in tight spaces. It gives you a better ability to have a tight bend radius, and you have some more options in terms of what kind of gear ratios or sprocket ratios or timing pulley ratios that you're using in using the belt drive. So that's what I would consider for that. The next question that I see is, just a minute, anonymous attendee, any predictions on the game this year? Yes, I have one prediction. It will be called Ultimate Goal. That will be the prediction that I give for the game this year. Beyond that, I can also just predict that it will be a field that could be easily divided in half because we'll have teams that will be doing that. But those are the only predictions I can give at this time. Maddie Stevens from 14145 says, what program do you use to design your 3D parts, and which do you recommend for teams who only recently got a 3D printer? I use Fusion 360. Fusion 360 has been really good for me to use. It's been relatively easy for us to have our team members learn and use, and it has a lot of capabilities. The biggest one for us is that not only does it do 3D printed parts, but it can do computer-aided manufacturing, or CAM. And what that means is that we have a lot of custom plates that are on our robots. So let me just go to another slide here. Let's see if I have the slide handy here. So this is the Rover Ruckus robot, and you could see the plates. We didn't use normal brackets like you would buy from somewhere to hold the wheels and the motors. Those are custom plates that was cut on a CNC mill here at the robotics laboratory that we have. And so Fusion 360 makes that step really, really easy where other CAD programs don't. I've heard that Onshape CAD is a really good one. It's an online-based CAD tool. And then we had a presentation earlier this morning for another CAD environment. So there's lots of good ones. Some teams will start by learning with Tinkercad, which is supposedly has a nice, easy learning on curve. But Fusion 360 is what I'm still recommending at the moment. Although based on recommendations from other coaches, I'm planning to also look at Onshape. Okay. I think I went through all the questions that are there. I will turn it over to the hosts and moderators again, because I think I went over time a little bit. And if there are any more questions, feel free to go ahead and throw them into the Q&A form, and I'll answer them for you in the Q&A form for a little while. Or you can always contact me online. You can go to the FTC7172.org site and contact the team there. You can contact me directly with my email or through the Google Group North Texas mailing list. Thanks a lot.
All right, thank you, Mr. McCod, for that very informative presentation. And now we are through the list of presenters for the beginner track. All that is left is to have the giveaway drawing, which will be a Go Builda 1121 series low side U channel bundle. So, and going by all of the team names and numbers that you put in the chat, I've created a wheel of names, and that's how we're going to decide who gets the prize. If only my computer could load, maybe.
Oh, Victor already have a wheel up, so.
All right, well then you can share your screen.
Okay, it's already shared. Yeah, well, like as Victor said, thanks to all of the attendees here, and we put it in the wheel, so now we're gonna spin it. Okay. So, congratulations to team 11472. In the chat, if you could please just claim your prize, then have one member of your team send a message to the panelists with your contact info, like the team number, the contact number, and in your email address.
Yeah, so if you can private chat one of the panelists, you could private chat Fang Wang 8565 or Parvel Gu 18227, your email address and email and your phone number, then we can get the prize to you. Congratulations.
Okay, now we're going to do the final drawing for the monitors that we're giving away based on the survey that you should have hopefully filled out. So once again, we're going to be giving you some used monitors donated by local tech companies. We have 5 of them to offer, but we're going to be drawing for 10 people in case some of the people who got a monitor don't want them. So if you're on the waiting list and someone above you doesn't want their monitor, then we can contact you next. Okay, here's the wheel of names, and I'll go ahead and spin it. Okay, number 21, that is Matthew Gonzalez, I think. So we already have your email. We collected it in the survey. So we'll contact you later for pickup thing, logistics and stuff. Okay, for the second winner, hey, number 3, that is Garrett Van Dyke. Congratulations, you can. Okay, number 6, that is Scott Roller. Let me just. Okay, number 17 is Justine Thomas. Number 18, Ariane Dom Lee, I think. Okay, number 2 is Maddie Stevens. Number 13 is Hemant Desai Pedanasani. Sorry if I pronounced your name wrong. Okay, number 4 is, I think, Corey Tells Chow. You only entered your name. You entered your email as your name in there, so I'm not sure. Okay, number 11 is Arav Mongol. And for the final winner of our use monitors drawing, number 9, Dana Harris. Okay, so if your winners number 1 through 5 or 6, you'll be winning a use monitor, and we'll contact you guys later. And if someone who's in those top 5 or 6 positions doesn't want a monitor, then we'll contact the next person on the list in order. So thank you for responding to our workshop survey.
Thank you all, and that's a busy day of a workshop. So we are going to meet again at the kickoff on September 12th at Patrick's online kickoff. For the videos, as soon as available, I'm thinking probably should be within this weekend. We will post to YouTube channel. So the channel name will be my team name, Technical Bots. And we will collect all the technical presentation slides in the afternoons and post to the same page you have been registering the workshop. So that's the PDF files will be there. Recordings will be on YouTube channel. We will provide a link from that page. Sure. I will also post to the FTC Google group. Feel free to leave if you don't have any more questions.